Hi, and welcome to the 7th tutorial video for this term. This tutorial has problems relating to rigid body motion. The first problem states, the circular cam of radius r is rotating clockwise with a constant angular velocity omega about the pin at O, which is at an eccentric distance e from the center of the cam. Determine the velocity and acceleration of the follower rod A as a function of theta. With problems involving a cam, the approach is generally to find an expression that describes the position of the follower, and then take the derivative with respect to time to find the velocity and acceleration. We're told that the cam is moving clockwise at a rate of omega, so we can say that theta dot is negative omega since the diagram shows us that theta is measured counterclockwise. The position of the follower, xa, is given by e cos theta plus r. If we take the time derivative, we find that the velocity is negative e theta dot sine theta. Substituting negative omega for theta dot gives us the expression e omega sine theta. If we take the time derivative again, we find an expression for the acceleration. Since theta dot is constant, theta double dot is 0. Making the same substitution as before for theta dot tells us that the acceleration of the follower is negative e omega squared cos theta. Now for problem 2. It states, the two-cylinder engine is designed so that the pistons are connected to the crankshaft BE using a master rod ABC and articulated rod AD. If the crankshaft is rotating at omega equals 30 radians per second, determine the velocities of the pistons C and D at the instant shown. I was reviewing the textbook solution, and I think there is a problem with the diagram. The distance from point B to point C should be 250 millimeters, so I've made that correction in the figure. With mechanisms such as this, you tend to consider each link individually. You tend to start from points where you have full information, and gradually solve your way through the system to find the velocity of the point that you're interested in. To do that, we're going to need the standard basis vectors that I mentioned in the previous video. I hat is positive rightwards, and j hat is positive upwards. The k hat vector points out of the page. When dealing with rigid bodies, there are two important things to realize. First, the absolute distance between 2 points on the rigid body will never change. Second, the rotation rate of the body is the same no matter where on the body you measure it from. We'll return to that second point later since it will become important in the analysis. Let's start with point E since we already know its velocity. Point E is connected to point B through a rigid link, so we can write this equation to find the velocity of point B. The velocity of E is 0, and the velocity of point B relative to point E is omega cross r. Working through the math, and we find that point B is moving left at 1.5 meters per second. We're done with link EB, so we can move on to link ABC. We just found the velocity of point B, so that's where we'll be starting from. However, we have a choice here. We can try to analyze point A first, or point C. We should pick point C since we know more about it to begin with. We know that point C can only move along the slot, but the velocity of point A doesn't have that constraint. We can use the same equation, but this time we'll have to make some assumptions. I will assume that point C is moving up the slot. If I'm wrong, I'll just find a negative velocity. Similarly, I'm going to assume that the rotation of link ABC is counterclockwise. To expand this equation, we can break VC into its I and j components. If I had instead assumed that the velocity of C was down the slot, I would have a negative sign in front of both of the VC terms since it would be moving in the negative I and j directions. We can also write omega ABC as its magnitude times k hat, following our assumption that omega is in the positive k direction. After expanding this equation out, we can gather terms in I and j separately. This gives us two equations for two unknowns. Solving this system tells us that the magnitude of VC is negative 0.776 meters per second, and the magnitude of omega is negative 4.39 radians per second. Since we found that the magnitude is negative, it means that our initial assumption about the directions of these two vectors were wrong. Point C is actually moving down the slot, and the link is rotating clockwise. Now that we know the rotation of link ABC, we can analyze the velocity of point A. This is what I meant when I said that the rotation rate of the body is the same no matter where on the body it's measured from. Points A and C are both rotating about point B at the same rate. By starting with point C, we could find the rotation rate of the body, and now we will use that information to find the velocity of point A. This one is pretty straightforward. simply substitute in the terms and solve. Note that omega is in the negative k direction since we found that the body is rotating clockwise. Point A is shared with link AD, so we can use its velocity to find the velocity of point D. Again, we make some assumptions about the direction of motion and rotation. I'm going to again assume that point D is moving up the slot, and the body is rotating counterclockwise. We follow the same procedure as before. And gather terms in I and j directions. Solving this system tells us that point D is moving up the slot at 1.06 meters per second. This time, we were still wrong about our assumed rotation direction, but we were right about the assumed velocity of point D. Lastly, we have problem 3. It states, if the slider block A is moving downwards at VA equals 4 meters per second, determine the velocity of block C at the instant shown. This problem is pretty similar to problem 2. I actually think it's a little bit easier. We start from point A and analyze point B since its velocity is constrained. I'm going to assume that point B is moving rightwards, and the rotation is clockwise. Point A has a velocity of negative 4j. Remember that because of our assumed direction of rotation, we include a negative sign in front of the magnitude of omega. Both of my assumptions turned out to be correct, and we can find the rotation rate. Now that we have the rotation rate, we can find the velocity of point D. Point D is shared with link CDE, so we can use it to find the velocity of point C. I assume that the velocity of point C is leftwards, and the rotation of link CDE is clockwise. Remember, the direction that you assume doesn't matter, as long as you account for it correctly when you're expanding the expression. We chug through all the math, and we get our answer. It looks like our assumption was wrong. Point C is actually moving to the right. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.